Okay, so today we'll discuss this 2018 October Edexcel paper. So this is from the unit one, which I gave you all last week. Okay, so let's look at this question. Which of the following, first let's discuss the MCQs and then go to the theory part. Which of the following quantities could have units of Newton meter per second? So if you get a question like this, we cannot do these sorts of questions by just memorizing. Okay, so it is Newton meter per second. So how to do a question like this? So first of all, one way is we should take each option and check the units of each option. Okay, so if you take gravitational field strength, it is a field strength. This is what we call as G. Also, it is an acceleration. It can be also known to be an acceleration, right? So its units will be ms minus 2, and it is not equal to Newton meter s minus 1, because these two are two different things. These two are two different things, and there is no Newton included here as well. Okay, so gravitational potential energy. So this is an energy. Okay, and we know that energy is mgh. Right? We know that energy is equal to mgh. Okay, so we get kg. This gravitational acceleration's unit is ms minus 2. Heights units are meters. So we get kg m squared s minus 2. Okay, but there's a small problem. That is like, even if we get this kgm squared s minus 2, we cannot compare nms minus 1 with kgm squared s minus 2. What is the reason? We cannot compare like that. Okay, that is because, like if you take kg, wait a minute. If you take kg m squared s minus 2, there is no Newton included here, right? So for energy, if you want to compare with this nms minus 1, you should include the Newton within this. Okay, you should include a Newton, the units for Newton inside this uh, equation. So how can you do that? We know Newtons, that means a force, right? We know that force is equal to mass into acceleration. So the units of force is kg ms minus 2. Now using this one, we can like include this thing inside this. Okay, so we have kg m squared s minus 2, which can be written as kg ms minus 2 multiplied by m. So instead of this kg ms minus 2, I can put Newtons. That's easy, right? So I can say energy is equal to what? Instead of like kg m squared s minus 2, I can say it is Newton meter, Nm. And Nm is also not equal to Nm s minus 1. Okay. And then we'll look at this thing, power, right? Power, we can take this equation directly, force into velocity, that is Newton's ms minus 1. Okay, so that is the correct answer. Or else you can take power is equal to energy over time, and we found that energy is equal to Newton meter divided by time is second, so that is also equal to nms minus 1. Okay, so power has the correct units. What you should note down is, when you get the units, there should be a Newton included inside the options. So in gravitational field strength, we couldn't include Newtons because like it's just an acceleration. But in others where there is energy, power, we should include the Newton. So that's what I did here. I included Newton somehow. Work done means what? Work done means force into distance. So that is Newton meter. So the correct answer is power. Okay. So you can pause this and watch. Like if you didn't understand, you can take some time, pause and understand it. Let's look at this. The equation delta W equals F delta S can be used to calculate the work done on an object by a force. Each quantity in the equation can be described as either vector or scale. Select the row from the table. Okay, select the row from the table that correctly describes each of the quantities in this equation. Okay, which is the row that correctly describes each of the quantities in this equation? Right. So we have discussed this sort of question in the earlier paper as well, as I remember. So we know obviously force. Force is a vector. That thing we know. And here S means displacement. So that is also a vector. Therefore, what are the possible answers? B, which is vector for force and displacement, and a scalar for the work done. And then you have D, which is including all three as vectors. So what is the correct one? Work done. So W means work done. So work done is just an energy. Work done is just an energy. It doesn't have a direction. Okay, it doesn't have a direction. We discussed this concept earlier as well. Work done, I mean power, gravitational potential energy, kinetic energy. So energy is a matter type of quantity. It's not a direction quantity. So we get the answer as what? A. Right? Sorry, yeah, it's B. Vector, and this is scale. Okay. Then let's look at the third one. A spring is suspended from a bar. A load of 2.5 Newton is added to the free end of the spring. Yes, that one, both of you have done it correctly. Yeah. So, might not need to discuss. That's a very simple question. You should just put F equals Kx and get this extension, and then like we can just put it right. We can just uh, oh no, let's do that. Like when it is 2.5 Newton, it has stretched by 4 centimeters. So F is equal to Kx. So 2.5 is equal to K times 4, and 10 is equal to K times X. Yeah, it's easy. Right? We can divide these two. So 10 over 2.5 is equal to X over 4. Therefore, this, yeah, I mean, I took this as total extension. Okay, this is the total extension. So I get X is equal to 16. It is the total extension. I mean, starting from the initial length up to this point, that's the total extension, 16 centimeters. So if you subtract this 4, you will get 12 centimeters. Okay, so this is the answer. Both of you have done that correctly, right? And then this question: a student takes measurements to determine the density of a metal in the form of a long thin wire. Which of the equipment should he use? So when you talk about density, density, right? So the thing is, um, density is given by mass or volume. So you should be able to measure the mass of this metal, long metal wire, and you should be able to measure the volume of this metal wire. So if you take a metal wire, it's something like this. So if you want to find the volume of this metal wire, right? If you want to find the volume of this metal wire, what we can do is we can take length and we can take this cross-section area. That is the normal way of measuring the volume, right? We take the cross-sectional area and we multiply it by the length. So to measure the mass, first of all, you should have the top band balance. This should be definitely available. Okay, you should have this top band balance. And then to measure the cross-sectional area, what can we use? To measure the cross-sectional area, what can we use? This is a thin wire. So they have explicitly mentioned that this is a thin wire. So if it is a thin wire, the best instrument to use is micrometer. Okay. Now let's say like this: to measure the mass, we have the balance. That's done. And to measure the length, okay, to measure the length, we have the, it's a long wire, so we should have the meter ruler. Okay. And to measure the cross-section area, we can either have micrometer or else we can have vernier caliper. It can be both of them. Both of them are theoretically possible. Okay. So The thing is, if you take the accuracy of a micrometer, it's generally in the 0.01 millimeter range. And the vernier caliper is generally in the 0.1 millimeter range. So the accuracy of the micrometer is greater than the accuracy of the vernier caliper. So you have two options: top band balance, meter ruler, micrometer, or top band balance, meter ruler, and vernier caliper. In case if you didn't remember, still you should be able to put this option because this is the best option. Right? This is the best option. And actually, it is more convenient to measure the thickness, measure the cross-section area of a wire using a micrometer. What we actually do is we use the micrometer and we measure the diameter of the wire. We measure the diameter of the wire first of all right? And then we can take the radius. We can take the radius by dividing the diameter by 2 because in a circle, radius is equal to the diameter divided by 2. And then we can use the equation pi r squared, which is pi times d by 2. We can measure the area finally. Okay, so that is the situation in this one. Top and balance, meter rule, and micrometer can be used. Vertical caliper is also like it's not theoretically wrong. It's okay, but this is the best option. Right. Next fifth question. The fifth question you have mistaken. A box is pulled up a ramp using a rope as shown. Okay. Um, the box moves at a constant speed. Forces acting on the box are weight of the box, friction force. See the diagram which represents the free body diagram of the box. So yeah, if you take this box, there is tension acting over here because it tries to move down and the rope is trying to pull it upwards. Therefore, there is tension. And then you have weight. You have weight. And you have a normal reaction. Like normal reaction is always, or normal contact force is always perpendicular to the surface. So this is the surface. This is our surface. So perpendicular to the surface means something like this, right? So this is the normal reaction, normal contact force. And then uh, the box is going down. Okay. Yeah. Now the box is pulled upwards, right? Like box is trying to go down due to gravity, but the box is pulled upwards. Since we are the direction of motion is this way, round, so we have friction to the opposite way. Did you understand that? Like the direction of motion is upwards, therefore the friction is downwards. If the direction of motion is downwards, the friction will be acting upwards. Friction is always opposite to the direction of motion. So you should get an answer like R should be perpendicular, T this way, friction this way, and W this way, right? Okay. Now we are sure that these two are not valid options. Like for sure, they are not the correct options, right? Obviously, reaction should be perpendicular to the surface and other forces should act like this. So now we are left with two options. We are left with two options. What are those two options? Either A or either C. So how to select the correct one out of A and C? Okay. So the thing is this. Now, this is a very important point. Like here you can see like, zoom this. Yeah. Here you might observe that here, like here this length is longer than this length. Here these two are equal. Okay. Right. Now, let me put this value as theta. And I'm going to find the forces which are along this plane, which are in this direction, right? Not this direction. Find the forces along this inclined plane. Okay, so first of all, I'll resolve this W. So here you get W sine theta. Here you get W cos theta. Okay, so they have told that the object is moved at constant speed. Object is moved at constant speed. So what does that mean? Object being moved at constant speed means the object doesn't have any resultant force acting on it. Okay, so if you take the inclined plane, it will not have any resultant force acting in this direction as well. Now take an object like this. If it is in equilibrium, surely the upward forces should be equal to the downward force. The left side forces, right side forces should be equal to the left side forces. Forces in this direction should be equal to the forces in this direction. Okay. So similarly, uh, if you take this diagram as well, so forces to this direction should be equal to forces to this direction. Okay. So forces to this direction are what? F plus W cos theta should be equal to T. Okay. So what does that mean? T is equal to F plus W cos theta. That means you should take the frictional force F and you should add a certain another force, and then only it will become equal to T. So this means T is surely greater than F. T is surely greater than F. Therefore, this will be the answer. Because as you can see in this C diagram, both are almost equal, but not in A. Okay. So the answer should be A. If you find any doubts, you can just go back and watch the explanation again. Okay. Right. Then we have this question. A small sphere of volume V falls at terminal velocity through a liquid. Okay. Right. Falls at terminal velocity V through a liquid. The largest sphere of volume 8 is made of a different material. The largest sphere falls through the same liquid at the same terminal velocity. Frictional force acting on the small sphere is F. Which of the following is the frictional force acting on the large sphere? Okay. So viscosity is given. Um, so what are the data? First of all, let's write the data. We have a small sphere. Its volume is V. Okay. And let's say made of material A. Okay. And then if you take the large sphere, and here the other thing is the same with terminal velocity. Right? Let's say the velocity, terminal velocity we take as U. Let's say. Okay. So if you take the large sphere, its volume is 8V, and it's made of, let's say, material B, and its terminal velocity is the same, right? Large sphere falls to the liquid at the same terminal velocity. Which of the following is the frictional force acting on the largest sphere? Okay. So this one, so here, here like now here they have meant by the frictional force, it's the viscous force. We should take like that in this question. It's not a little, not that much clear, but like if you take water friction, that is actually viscous force, right? Nothing else. So uh, here we can say friction force acting on a small sphere is F. So let's say now the small sphere is something like this with the volume V and the large sphere has a volume 8V. Okay. So frictional force acting on the small sphere is, we know, 6 pi eta RV. Right? Let's say the small sphere's radius is equal to R. Say the small sphere's radius is equal to R. If so, what is the radius of the large sphere? That's the problem. What is the radius of the large sphere? Let's see. We know small sphere's radius is R. That means V is equal to 4 over 3 pi R cube. Large sphere's radius, let's say capital R. 8V is equal to 4 over 3 pi times capital R cube. We don't know exactly. We just take it like this. Okay, we can tell like this. And then we can do 2 divided by 1. I'm going to divide the two equations. Okay, I'm going to divide the two equations and I get 8v over v equals 4 over 3 pi capital R cube over 4 over 3 pi simple R cube. So I get 8 simple R cube is equal to capital R cube. This one you can see, we can write it as 2R cube is equal to capital R cube, which means the capital R is equal to 2R. Okay, that's a simple max part. And then we can say force on the largest sphere is equal to 6 pi eta 2R V. So this is 3 and this is 4. And I can divide these two, 4 divided by 3. Force on the largest sphere divided by force on the smallest sphere is given as F is equal to 6 pi eta 2RV over 6 pi eta RV. So VV 6 pi eta eta. Therefore, force on the largest sphere is equal to 2F. I hope you understood this. Okay. So I'll clear this. If the liquid is cooled, the terminal velocity of the sphere would change. Terminal of the sphere would, what happens? If the liquid is cooled, right? If a certain liquid is cooled, what will happen to the terminal velocity of the sphere? We can think about it, right? So liquid cooled means the viscosity would increase surely, right? That means if you take a certain liquid which is heated, then the viscosity would decrease or the frictional nature of the liquid will decrease. And if the liquid is cooled, the frictional nature of the liquid would increase, surely, right? So here we can um, say eta would surely increase. Okay, it will increase because it's cooled. And what will happen to the terminal velocity? We know the equation V is equal to 2r squared g rho naught minus rho L over 9 eta. So this thing increasing means this thing decreasing. So eta would increase surely and it will decrease the terminal velocity. So B will be the answer. Okay. Right. So you have done that correctly as well. Let's go to the next question. Ball takes 1.6 seconds to reach the ground. From what height was the ball dropped? How can you do that? That also you will have done correctly. Right. You can do put the sweat concept and then find which quantity is missing and then you can do it. Right. So that is done correctly. And then ninth one also done correctly. Which is following is the velocity time graph motion of the ball. So let's look at this. Now here a ball is just dropped, right? Ball is just dropped. And yeah, it falls down. Okay, it is dropped and it just falls down. Goes dropped and is caught after the first bounce and then it bounces. It is then caught at this point. Okay. So like throughout this motion, right? Throughout this motion, we obviously know that the gradient is equal to the acceleration. That is a concept in velocity time graphs. And we know that this acceleration is equal to g. I mean, regardless of whether it is falling downwards or upwards, always this acceleration is equal to g. Okay. So the gradient of the graph should be constant. So this is a wrong answer, wrong option. Okay. And another thing we know is, let's say the downwards is positive. Therefore, first when the ball is moving downwards, we know the velocity is increasing positively, right? Velocity increases. Obvious, right? If downwards is positive, surely the velocity increases positively. That means what? That means what? And increases positively and constantly, right? Okay. So surely velocity should increase positively and the gradient is constant. So there should be a constant gradient and velocity should increase positively. See, it should be something like this or this. It cannot be this thing as well. Now we are left with only two options. It should increase. And then after bouncing back, it should change its direction. So now you have a positively increasing velocity. It comes up to a certain point. And then after bouncing back, it suddenly shifts to negative. And then again, it goes upwards because there should be the same gradient. So what's the answer? Is it C or is it D? It should surely be D, right? Because the reason is when the ball comes downwards, let's say when it comes downwards, it achieves a velocity, let's say 20. And when it bounces back, it is not going exactly with 20. It should be something like 15 because a certain amount of kinetic energy is absorbed by the ground due to this collision, right? So surely this should be like this value should be greater. The value in which it comes down and the value in which it goes up should be low. Okay, so the answer should be D part. Right. Then let's go to the 10th question. If two liquids of different viscosities flow through identical pipes, if the conditions are identical, the liquid with low viscosity will. Yeah. So what's the answer for this? Two liquids with different viscosity flow identical conditions. Yeah. So obviously, if the viscosity is lower, that means the friction is lower, right? Viscosity lower means friction lower. So if the friction is lower, it can move at high speed, right? Now think about something like this sauce flowing inside the water pipe and water flowing inside the water pipe. So water will flow at a higher speed and transfer greater volume of liquid per second. So this should be the answer. It's a very sort of common sense question. Right? You've done that correctly. Okay, so now let's go to the section B. So first of all, they're asking what is meant by. Now this one will compare the answers and right. What is meant by gravitational field strength? Okay, so gravitational field strength, like the actual definition is like these things we are going to cover in the fields lesson, but I mean, we look at the definition, right? It is equal to the gravitational. For now, just remember the definition: gravitational force per unit mass. Gravitational force per unit mass. Right? Let's see here. Yeah. It's a gravitational force per unit mass exerted on an object, or the gravitational force per kilogram. Right? Just remember the gravitational field strength definition is gravitational force per unit mass. Equation wise, we can see later how this thing actually comes. I mean, within our range, we have this equation, right? We know W is equal to mg. So this G is the gravitational field strength. So G is equal to W over M. We can say it is the weight per unit mass or the gravitational force per unit mass. Because if you have something like, let's say density is equal to mass over volume, the meaning of this definition is mass per unit volume. This thing per unit, I mean numerator per unit denominator. Okay. So the speed equals distance or time. Distance per unit time. Similarly, G is equal to W over M. Weight or the gravitational force per unit mass. But in the phase lesson later on, we'll see exactly how we get this equation. Okay. Right. And then in the next question, they are asking center of gravity. So center of gravity meaning, a point at which all weight of an object can be assumed to act. Right. Or the point at which all weight is centered upon. These answers are correct. Okay. Right. Next question. The gravitational field strength on Earth is 9.81. Show that this results in an acceleration of free fall of 9.81. Okay. So here, yeah, that's a very simple proof, right? So they are telling that the gravitational field strength is 9.81. If so, tell us that acceleration is also 9.8. This is something that we already know, but let's see how to prove that. If you take an object, and if it is like falling down, if there's no air resistance, if you assume there's no air resistance, we can say the force acting on this object, if this is a mass, is m. Force acting downwards is mg. So we can put F is equal to ma downwards. Therefore, we get mg is equal to ma. So we get A is equal to G. It's a very simple like proof, right? Just two lines. It's a very simple proof. Okay, so that's all about the 11th question. That's very easy. Then let's go to the 12th question. Two students carry out experiments to measure the acceleration of free fall. In each experiment, a ball bearing is dropped through a known distance and the time is measured. Student A drops the ball bearing and starts the stopwatch. He stops the stopwatch when he sees the ball bearing reaching the ground. The stopwatch measures to the nearest 0.01. Okay, yeah. So what they do is they just drop a ball bearing from a certain height, and it's a known height. Okay, it is a known distance, and we can measure the time. And using the time and the distance, what can we do? We can measure the acceleration of free fall. I'll first say how we can do that exactly. Now, you have time, you have the distance moved, okay, which is displacement. You don't have the final velocity. Okay, you don't have the final velocity. Drop means you know the initial velocity is equal to 0. Okay, so you don't have the final velocity means we should use the equation s equal to ut plus half at squared. So we can say s is equal to ut. I mean, since u is equal to 0, ut will get cancelled. Half at squared. So we can say a is equal to 2s over t squared. So what can we do? We can like measure the distance, which is actually known before doing the experiment because it is a known distance they have mentioned in the paragraph. And we can measure the time using a stopwatch. And using these two quantities, you can get the acceleration. That's simply the practice. Okay. So student B uses an electronic system that releases the ball bearing and simultaneously starts a timer. The timer stops automatically when the ball bearing reaches a sensor. State and explain two reasons why method of student B is better. Okay, so like the first point that should get to your mind is the electronic system, right? So if you take an electronic system, it is more accurate. So that's one thing. Electronic system is more accurate. Okay, and the timer is automatically stopped. So stopping by using a sensor is very quick and very accurate than a human stopping it. Okay, so that's one thing. So let's see the points here. Uh, Reaction time for stopwatch or no reaction time for electronic timing system. Okay, so they have asked state and explain. See, state and explain. So to get the 4 marks, what you should do is you should state one thing. You should give the reason. You should state another thing. You should give the reason. If you do that just for 2 points, like you take 2 points, you state the 2 points, and then you explain the 2 points, then you will definitely get 4 marks. See, you can see it. Reaction time for stopwatch or no reaction time for electronic timing system. Explanation is reaction time is large compared to the time to be measured. Yeah, we can say like that because the time to be measured is like to the nearest 0.01. So reaction time might be something like 0.5 or like, yeah, 1 second, like that. So it's not good. Okay. So it's better to use the electronic system. Okay. And then another point is smaller percentage uncertainty. Yeah. So if you use the electronic system, see, if you use the electronic system, now I'll explain that. Now, if you use the electronic system, the thing is, it has accuracy. It has accuracy of 0.001. Here you have only 0.01. Now, what is the specialty in this accuracy rather than this one? What is the specialty? Okay. Now let's say it's like this. Let's say the actual time taken for this process. The actual time taken for this process, let's say it is 4.583 seconds. Just an example to explain you the concept. That's the actual time. Okay. But when student A measures this, right? Student A measures this. Since his stopwatch is measuring to the nearest this thing, he might measure something like 4.58 seconds. Since the student B's timing is up to this accuracy or up to this precision, so we can say student B would measure something like 4.583 seconds. Okay. In case if there's a certain delay of this electronic timer or electronic system, it might be something like 5.82 seconds or 4.8584 seconds. One up and one down. But if there's a delay in this thing, If there's a delay in this thing, it would be something like 4.57 seconds or 4.59 seconds. So if you write it in three decimal places, it's 570,590. Now can you see, like, this is erroneous. This is more erroneous, right? It has a higher percentage error. This has a lower percentage error. This has a higher percentage error, and this has a lower percentage error. See, the correct one is 583. If you get 582 or 584, that is no issue. And the correct one is 583. And if you get something like 570, 590, that's a very large gap. Okay. So that's what is explained by this point. Okay. Hope you understand that. Yeah. Timer started after ball released or ball released with the force. Initial velocity not zero or measured time would be lower. Yeah. And small percentage answer. Okay? Yeah. Because since the timer, there's more, the time is more error prone, right? That's the reason. Initial velocity not zero. Measured time would be low. Yeah, since this thing is dropped, that's also one point. Like, so the electronic system releases the ball bearing, but student A will drop the ball bearing. So when you drop the ball bearing, that there can be an error. Like sometimes the initial velocity might have a certain small value, but using an electronic system which will release the ball bearing, that issue is clarified. Now let's go to the 13th. Okay, so this is a good question. So let's look at this. A crane is used to remove an object from the bottom of a lake. Okay, there's a big crane. It's removing an object from the bottom of the lake. The object is a cylinder of height h, and the depth of the lake is capital D. The cylinder is moved vertically through the water at a slow and steady speed. The cylinder comes to rest in a position where it is completely above the surface of the water. Okay, so it is being lifted upwards. And now we are going to look at the tension variation. Okay, now let's see how why tension varies like this. So here you have tension. Okay, so yeah, at one moment it gradually increases and then it again remains same. Okay, so let's take the two, like classify this question into two parts. Inside board. Inside water, what is the tension? Hmm? You have tension, weight, and upwards you have a, since this is pulled upwards, um, yeah, you have upthrust, right? Upthrust. So, in the T plus U equals W. So, T equals W minus U. It is inside the water. Now, let's look at this thing. On the surface. The surface, what is it? So, on the surface, it is partially immersed. Okay, let's say the upthrust is U and there is tension upwards and there is weight downwards. So here also let's say T equals W plus U. So T plus U equals W, right? T is equal to W minus. But the thing is, U decreases gradually because if you take the lake, if the what you call what the cylinder is here, let's say the upthrust is 10. If the cylinder is a position like this, what will be the upthrust? It will be low. It will be something like 2. That means just as you lift the cylinder above the surface, the upthrust will decrease. See, upthrust will decrease and the tension will increase. Right? The upthrust will decrease little by little. Since the volume immerse will be lower when you just lift it up. Therefore, the tension will increase according to this equation. So that is the stage represented here. Right? Tension will increase little by little, and when it comes out of the surface, you can say by equilibrium tension is equal to W. That's the thing about the whole thing about this question. Right? Okay. So you should neglect effects of viscosity here because normally if it is not a sphere, we don't consider viscosity. Okay. So they're asking state expressions for the distances P and Q. So what is the distance P? Hmm? Distance P means distance moved by the cylinder. So this is the distance moved by the cylinder in this uh, x-axis. So if the cylinder has moved a distance p, that means when it had moved a distance p, the cylinder is in a position like this. Am I correct? Because it's starting to come out of the surface. Okay. So the top of the cylinder was initially at this place, and now the top of the cylinder is initially at this place. So what is the distance moved here? It is d minus h. Okay. Because p is the point where the cylinder comes to the surface. So this is d minus h. Right? Distance q means it had it had moved out of the surface. Right? So if you take distance q, it is something like this. The bottom of the cylinder was here. Now the bottom of the cylinder is here. See, so the bottom had moved a distance d. This is d. If you take distance p, that means the top of the cylinder was here. Now the top of the cylinder is somewhere here. So the top of the cylinder has moved a distance d minus h. The bottom of the cylinder has moved a distance d when you come to q. Okay. So if you take the distance moved by the top part of the cylinder, that is equal to the distance moved by the cylinder. If you take the distance moved by the bottom part of the cylinder, which is convenient to calculate q, that is the distance moved by the cylinder. Okay. So yeah, it is d minus h and d. Right. And then we'll look at this thing. Explain the shape of the graph. So you can do that explanation, right? What I told earlier. Statement of resistance. Tension equals weight minus upthrust. Initially tension constant as upthrust is constant. Like yeah, so upthrust is constant. Therefore, tension is equal to W minus U. Therefore, yeah, it has a constant tension. Yeah, speed is slow. So they have this is an external point. Like if you write now, there are 5 marks and you have 6 points. So this point is an external one. If you write it, you'll get a mark because they have told that it is moved slowly, right? Slow and steady speed. Therefore, we can like when it is moved very slowly, the friction force encountered is a little bit low. As the cylinder moves to the surface of the water, see volume or the weight of the mat displaced decreases because it comes out little by little. Therefore, due to that, the upthrust decreases, and due to the decrement of the upthrust, the tension will increase. That's what I told earlier. You can refer, go back and refer that. Okay. So tension increases as upthrust is proportional to submerged volume. And then when you come above the water surface, tension is equal to weight, which is much higher than tension being equal to weight minus upthrust. Okay, so that's it. So if spacecraft are used to carry new samples, okay, they have to tell something. During takeoff, combustion produces hot gas at a very high pressure. The gas expand and move downwards out of the rocket. Explain how this enables this aircraft to accelerate away from the ground. So when the gases move downwards, okay, so gases moving downwards means there is a force exerted by the gas, by the rocket on the gas. Hot gases exerted an upward force on the spacecraft. There is now a resultant force upwards greater than V. That's why it moves. Right? Actually, this is what happens. So yeah, so here there's a force acting on the gas by the rocket. Acting on the therefore there's a reaction force acting on the rocket by the gas. Now, if you consider the aircraft alone, you have a force upward acting on the rocket by the gas, and you have a force downward acting on the rocket by the earth. This is acting on the gas, okay? We don't need to care about this. Now I'm considering only the forces acting on the only forces on rocket. Okay. So move down. So, explain how this enables spacecraft to accelerate away from the ground. So if this FRG becomes greater than FRE, acting on the downward weight, this is also known as weight. Okay. Then this rocket can move upwards. So there should be a very high pressure to move this. Like, just think about the mass of the weight of a rocket. Okay, you can even believe the weight of a rocket. It's a very large structure, right? So you should have a very high force generated from the combustion of these gases to move them upwards. Okay. As a spacecraft takes off, the apparent weight of a crew member is 3,700. Determine the acceleration. Right. So this one I'll explain. Mass of the crew member. When you do the paper, I thought I missed a point. Like, so here there's a crew member. So the apparent weight. Now, first of all, let's talk about this apparent weight concept. Now, let's say you are standing here. Let's say something is moving upwards with an acceleration A. Then you have this normal contact force. That is R, and you have the weight downwards. So if you apply upward F equals ma, you can say R minus W equals ma. R equals ma plus W means mg. Weight is mg, right? So R is equal to m times g plus a. Okay. Right. So this is what you call as the apparent weight. Okay. Let's take a situation like this. Yeah. A certain there's reaction, there's weight. A certain system is moving downwards with acceleration a. It's moving downwards with acceleration a. If so, we can say F equals ma downwards. W minus R is equal to ma. R is equal to W minus ma, which is equal to, this is mg, right? So m times g minus a. This is the apparent weight here. So that's obvious, right? If you move upwards in a lift, you will feel more weight. You will feel a greater reaction force. You will feel more weight. Now, the important thing is, when I say you will feel more weight, that is, I mean, I'm talking about the reaction force. And when you move down a lift, you will feel less weight. Again, I'm talking about the reaction force, because, like, if you take a person, if you take a living thing or anything, like if you take an object, right, the magnitude of weight felt on that object is determined by the reaction force. Okay, it is determined by the reaction force, right? Like, only when we stand on the floor we can feel the weight due to the reaction force. So here also the apparent weight means this is the reaction force. It is felt by this crew member. Okay. So now we can calculate the acceleration of the spacecraft. This is R. Let's see. This is mg, and the spacecraft is moving upwards. Okay. Then acceleration a. So we can say F equals ma. R upwards we put R minus mg is equal to ma. So we know R is 3,700. The mass of the, what you call, the crew member is 81 into, this is 9.81. The mass of the, now we are putting for the crew member, right? We are putting F equals ma for the crew member. Okay. So crew member, I told you that the crew member will also have the acceleration of the spacecraft, because they are in the same system. If you're traveling in a vehicle, um, actually you are also having the acceleration as same as the vehicle, right? It's simple as that. So here this we have put for the crew member, so this m should be 81 into a. Okay, so if you calculate this, now let's calculate this. So 3,781 into 9.81. 81 into 9.81, that is 794.61. Yeah, it's almost 36. I hope you understood that. We just put F equals ma for the crew member. And crew member is inside the spacecraft. Therefore, he will also feel the acceleration of the spacecraft. And apparent weight means the reaction force. Simple as that. Okay. As each fuel tank becomes empty, the tank and its associated rocket are detached from the spacecraft and fall back towards Earth. Yeah, so when the fuel tank becomes empty, like the rocket cannot retain its initial force exerted due to the gases. Therefore, like it should have another compensation mechanism to balance that weight. Now, it's like this. Let's say initially the rocket had a weight of 1000 newtons and the fuel supplied a weight of 1200 newtons. Therefore, we were able to like accelerate and reach a certain speed. That's true. But as you go up, the fuel becomes finished, right? Now the force exerted by the fuel will be something like 500 newton because we don't have much fuel. It will end at one moment. Okay. Sorry. I have done mistakenly. This is the force exerted from the fuel. This is the weight. Okay. Now let's say after going some distance, this thing becomes 500. And let's say still the weight is 1000. What will happen? The rocket will again fall down. It will go up like just like a projectile. It will go up and then it will fall down. Right. So to compensate that, what we should do is we should decrease this 1000 as well. Let's say if we are able to decrease this up to like 400 by dropping the unnecessary components, right? So by especially we can drop the fuel tank, right? Okay. So by dropping the fuel tank, we can manage that. So let's see how the answer is written. That's the concept behind this. This reduces the mass of the spacecraft, so acceleration will decrease. As simple as that. When the capsule returns from international space, parachutes are used to reduce the speed of the capsule as it nears the surface of the Earth. Explain how the parachute reduces speed. Now that's also easy. I think you have answered this. Both of you have answered that properly, but have not got all the marks. Yeah, you have not got all the marks because these points should be mentioned. When the parachute is when parachutes are used, what happens? There's a sudden increase of surface area, so that will increase the viscous drag, air resistance drag. Okay, so then it will exert an upward resultant force, which will in return decrease the speed. You should explain it like a story. That's the beauty of these questions. When you use a parachute, it will increase the air resistance or the drag force. So due to that increment, okay, there might be a resultant force upwards, or the resultant force will decrease downwards. Like this time, the parachute will have initially weight 100. When you put the parachute, this will go up to like 120. So the resultant force downward will decrease. Okay, so that will in return decrease the velocity or the speed. That's what you should take. Parachute has a large increased cross-sectional area. So that was said by like, both of you have said that point. Air resistance or drag force increases. Resultant force is now upwards. That's also enough. Okay. So if you tell velocity has decreased, that's also fine. So these 3 points should be definitely mentioned. Okay. It's very nice if you can write them as a story. Just think it as a story and then write them. Right. Yeah, these questions will do. Now let's look at the 15th question. They are told that projectile A is launched with the velocity UA at an angle theta to the horizontal. Okay, this should be theta. UB at an angle 45. Show that UA may be expressed in terms of UB like this. Another thing is this. So if you take the horizontal velocities of UA, you have UA cos theta, and in UB you have UB cos 45. Now you know the horizontal velocities are these things. So you can see cos theta in the expression they have given. Okay, so like then I mean, as a physics student who have done a lot of physics questions, you should feel like okay, then there is something related to the horizontal component when I do this question. Like those sorts of things you should feel intuitive. And that means like by intuition you should feel those things. So here, so we know that, and what we can see is at time t. So at this point, same time and same horizontal distance. They have with same time, same horizontal distance. So what can we do? We can do something like this. We can apply s equals ut plus half at squared horizontally to both objects. Since horizontally there is no acceleration because there is no resultant force horizontally, we can say s equals ut. For a, we can say same distance, right? It is d, same. D is equal to u a cos theta times t. And for b, I can say d is equal to ub cos 45 multiplied by t. It's a very simple question. So you can take this 1, take this 2, then you can divide this to 1 over 2. D over D equals UA cos theta t divided by UB cos 45t. Yeah, so cos 45. You can find what is cos 45. Then you will get UA equals UB cos 45 divided by cos theta. And cos 45 is actually equal to 0.707. So UA is equal to 0.707 UB over cos theta. It's just a mathematical thing. Okay. Then on the axis below, sketch labeled graphs for the vertical component of velocity against time. Oh no, so second one we missed. Extend why the path for the paths of the two projectiles to be shown UA greater than UB. That's also very simple. Right? So we get the above expression UB equals cos theta. Okay. They are asking to show UA is greater than UB. So we can do it. It's sort of a mathematical inequality, right? Yeah. So here. We can do something like this. We can tell UA over UB. Therefore, this one we should think a little bit. Equals cos theta over cos 45. We actually don't know what is theta. We don't know what is theta. But we know something. What do we know? We know that theta is greater than 45. You know theta is greater than 45. That one obviously we know. Okay. If let's say you have two angles, you have 60 and 45. You know that 60 is greater than 45. But actually cos 60 is equal to 0.5 and cos 45 is equal to 0.77. If 60 is greater than 45, definitely cos 60 should be less than cos 45. That's how the cos function works, or the cosine function works like that. The cosine value of greater angles will be lower, and the cosine value of lower angles will be higher. Let's take, for example, 90 and is greater than 0. But cos 90 is equal to 0 and cos 0 is equal to 1. But cos 90 is less than cos 0. Similarly, theta greater than 45 means cos theta is less than cos 45. Okay. Therefore, we can say here cos theta is less than cos 45. Therefore, cos theta over cos 45 should be less than 1. Obvious, right? Cos theta over cos 45. If I tell cos theta is less than cos 45, I can write into 1 and take this theta down. I mean, divide everything by cos 45. This means cos theta, cos theta over cos 45 means UA over UB. Wait a minute. Sorry, I have done a mistake here. I'll do it from the beginning. Wait a minute. So here, I've done a small mistake. We get the initial equation UA equals 0.707 UB into cos theta. Okay. Okay. So I can say UA or UB. We know. So you can say UA. We know 45 is less than theta. Is it? Obvious, right? 45 is less than theta. Therefore, we can say cos 45 is greater than cos theta. Therefore, we can say cos 45 divided by cos theta is greater than. So cos 45 or cos theta means UA or UB. So UA or UB is greater than 1. Therefore, UA is greater than UB. The early one I did, I took the equation wrong. That's right. This is the correct. Okay, let's see how they have given this. They have also given the same thing, right? This is the correct this thing. This way you can understand. Oh. Okay, go to the next question. You can pause and understand this. On the axis below, sketch label graph of vertical mode of velocity against time for the motion of projectile A and projectile B between O and P. Yeah, so vertical component of velocity, if you take something like this. So, yeah, it depends, right? I mean, uh, which one has a greater vertical component of velocity? Hmm? How can you check that? This is how we check it. Initially, we have UA theta 45. Is that the correct one? Yeah, that's correct. Okay, UA at theta and UB at 45. And we got a relationship between them. What's the relationship? UA greater than UB. And the vertical you have UA sine theta. Here vertical you have UB sine 45. Okay. We know theta is greater than 45. So sine 1, if theta is greater than 45, sine theta is greater than sine 45. Cos 1, it is opposite. Okay. And also we know UA is also greater than UB. See, UA is greater than UB and sine theta is greater than sine 45. Surely then, these both sine theta and both sine theta and UA are greater than sine 45 and UB. So you can say UA sine theta is surely greater than UB sine 45. So UA sine theta has a greater velocity, initial velocity component, like this way. UB might be something like this. And they both of them have the same acceleration. So this should be the graph. This is sort of a mathematical question. You don't need to have much projectile knowledge, but it's sort of mathematical. Just refer the video again and understand. Yeah, in the second graph, they have taken the opposite direction. That is also correct, but it's better to draw the first graph given in the answer. Train consists of water droplets of different sizes. Explain why large droplets of rain reach the ground more quickly. You may assume that the upthrust acting on a raindrop is negligible. Yeah. No upthrust. There's a weight. There's a viscous force. Okay. This is a very simple question, right? We have discussed this concept many times. You all have written correct answers for that. Yeah, partially correct. So let's see how the correct answer. You know the concept behind this, right? So if the raindrop is very large, okay, it has a greater weight, right? So due to this greater weight, it takes more time for these larger raindrops to achieve terminal velocity because viscous force should increase more and more in order to achieve this condition. Therefore, since it takes a greater time to achieve terminal velocity, it moves a greater time with a certain acceleration. Thus, it falls down quickly. Okay. I mean, taking much more time to achieve terminal velocity means it falls quickly. Right? But if you take a smaller drop, it achieves terminal velocity very quickly. That means just after falling, it will achieve terminal velocity. If so, it will take more time to fall. So let's see how they have given the answer. At terminal velocity, the resultant force is zero. That should be stated. And it's better if you can state one of these equations. Terminal velocity is proportional to the radius squared. Yeah, this way also we can take. Larger droplets have greater terminal velocity. You can using the equation, you can directly take. V is equal to 2r squared g rho naught minus rho L 9 eta. Using that equation also, you can directly take. Or else you can say at terminal velocity resultant force is zero. Larger droplets require greater air resistance. See, larger droplets require greater air resistance to equal greater weight. So it increases more rapidly than that. So since they require greater air resistance, they will fall down quickly. Right? So you can refer this marking scheme and understand. You'll know this, like you can go in the equation way, that's easier, as I think. Or else you can go in the explanation way. So I have given marks according to these points. Right. Train is falling down 0.5 due to wind. The ice moving horizontally at speed 12, moving with the rain. Yeah, I think this one also both of you have done it perfectly. You have done. You got all the marks. Yeah. It's just a vector diagram. So when you draw the vector diagram, you should draw it like this way, or you can draw this way as well. No problem. No issue. Okay. And when you take the direction, that's an important thing. You draw a vector diagram like this. So when you take the direction, you should always measure the angle like this much angle to the horizontal. Because if you have fixed directions like north, south, east, west, then you can tell it is to the north, it is to the east, or something like that. But if it does not have a fixed direction, you should take the angle along with the horizontal. Then let's look at the 17th question. A guitar produces sound by making a series of strings vibrate. To produce the correct frequency of sound, tension in each string must be adjusted by a tuning peg. Okay, a new string is attached to the guitar and wound around the string. Okay. So yeah, let's look at the terms given. So this is also an easy question. This is not that difficult. So they have given the original length 0.60, tension 190, and extension 8. See, diameter this. Okay. So we know Young's modulus is equal to force over area, which is stress, divided by extension of initial length, which is strain. So we can say it is FL naught over AE. So they are asking, oh no, they are asking the extension. So then the string will extend by about 8 millimeters. So what can we do? We can subject extension here, right? You can say E is equal to FL naught over A by. So force 190, length percent 0.60. If you take cross-sectional area, so this is the diameter. Diameter is 3.3 into 10 to the power minus 4. So the radius is 2 into 10 to the power minus 4. So the area is pi r squared. We know that 2 times it is pi times this thing squared. You can plug in the value you get as area into this thing. And what's the Young's modulus? That is given 170 gigapascals means 10 to the power 9. Kilo means 3, mega means 6, giga means 9. So likewise, you can do the question. And yeah, don't do silly mistakes when doing these sorts of questions, right? There's a high chance that you might do silly mistakes, but be careful. Okay, so you'll get the value 8 meters. And do this question slowly. Don't be in a hurry. The rotating cylinder has a diameter of 9.2 into 10 to the power minus 3. Calculate the number of turns the rotating cylinder that are required to produce this extension. Yeah, so how can we calculate that? So, yeah, so this is the diameter. So, like if you roll the rotating cylinder to extend it, right? I mean to Like there's in the guitar, there's a string like this, and there's a like rotating plug sort of thing like this. When you tune the guitar, you use this. Okay. So it is said that the diameter is given. Okay, the diameter is given. So using the diameter, they're asking to find like how many turns we should turn this. Okay. So first of all, let's calculate the circumference of this one. Circumference is equal to 2 pi r, or we can say 2r means diameter, pi d, and we can get the circumference. Okay. And after taking the circumference, okay, so they're asking number of turns. We calculate the circumference. Um, yeah, that are required to produce this extension. So if we want to extend this by 8 millimeters, how much turns? How much turns? That's what they're asking. Okay. So we can say uh, one turn, one turn accounts for pi d amount of millimeters. How much turns? How much turns will account for, let's say, x, 8 millimeters. Okay, so we can say cross multiply 8 is equal to pi d into x is equal to 8 to pi d. Yeah. So let's see the answer. See, 8 to pi d. So it's 0.3 turns. Okay. Because like you should rotate it 8 millimeters. You should extend it by 8 millimeters, and when you do perform one turn, it will extend by pi d amount. So in order to like rotate it by 8 millimeters, you should do 8 divided by pi d, as explained by this thing. You can understand. Yes. It is important that guitars have high elastic limit. So this one you have done correctly. They should have high elastic limit because what's the reason? Maximum stress for which the material is returned to its original length. Right? What have they asked? They have asked the definition of elastic limit, right? Yeah, maximum stress in which the material will return to its original length. Explain why guitars should have a high elastic limit. That's the next question. Explain why they should have a high elastic limit. That's because like even with a larger tension, it will not permanently deform. Or like even when we apply a larger tension force, because when you play a guitar, you might need to apply very large forces, right? When you play it hard, like you are applying a lot of force. So even if the force is applied, it will still return to its original initial length. So that's the advantage of having a high elastic limit. Right? Guitar does not go out of tune. And when you have a high elastic limit, you can extend it and you can maintain the length of the guitar string as you want. Okay. So if you cannot do that, I mean, if you cannot maintain the length of the guitar string as you want, then it might go out of tune, because the frequency produced by a guitar string, later in waves lesson we'll discuss how that depends, like how the frequency, how the sound you hear depends on the length. It's sort of a different thing. Let's discuss that later. So simply, if you have a high elastic limit, it will not deform or it will not change its original length. Therefore, it will not go out of tune. Yeah. So you will have written that. Yeah, given marks. You will have mentioned the points. So that's good. And 18th one. In the spot of pole vaulting, long flexible pole is used to lift up it. Okay. That it runs down a narrow highway, speeds IP and places the end of the pole in the pole box. Pole bends and then straightens, moving the athlete up. At the maximum height, the athlete just go off the pole. Okay, explain how the pole using the pole enable the athlete to reach a crater. Now let's see. Yeah, you should explain in terms of energy transfer. This question most, yeah, both of you have not done it properly. Okay, this is a question with a large amount of marks. So let's see. So as the pole bends, kinetic energy is transferred to elastic potential energy. That's true, right? Now you are coming with the pole, and at all of a sudden you stop. And when you stop, that all that energy is transferred into the pole as elastic potential energy. So then the pole bends and then it straight, right? So like it's like this now. First of all, the pole will bend like this, and when it's straightened, what happens? This pole moves up. See, as this diagram implies. See, bends, and now as the pole tries to straighten up, what happens? That elastic potential energy is lost, and it is given, or it is converted as kinetic, as gravitational potential energy, because this this person, this athlete is increasing his height. Okay, greater heights can be reached as the EP stored in the pole is greater than in the legs when jumping. Yeah, exactly. Because when you jump, what do you do? When you jump, what we do is we use the energy stored or elastic potential energy or the chemical energy used stored in our legs to produce a certain gravitational potential energy and reach a certain height. Okay, that's what we do when we jump. We bend down and then we all of a sudden jump. Actually, the elastic potential energy within our muscles is converted to kinetic energy. But instead of our legs, if we can have a device which is like sort of better, uh, which has a greater elastic nature, then that is greater because greater heights can be reached as the elastic potential energy stored in the pole is greater than that of the legs. When compared to the legs, the pole is greater, pole is better, right? More of initial kinetic energy is transferred to the gravitational potential energy in the pole duality. That's true, right? So yeah, the pole is more. These points should be written. I hope you understood that. So using the pole rather than the leg is better. An athlete reaches max velocity 9.4 before placing power. Just horizontal velocity. Yeah. Okay, so it's like this. So here, this is an important question. So now the athlete is coming 9.4. And then this kinetic is energy is converted into elastic potential energy. And then all of this elastic potential at the maximum height, all of this elastic potential energy is converted into kinetic energy. I hope you understood this. The athlete is coming with a certain kinetic energy at 9.4 speed horizontally. This kinetic energy is all at a sudden stopped, converted to elastic potential energy. Then as the ball moves upwards, this elastic potential energy is converted into kinetic energy. So this was sort of an intermediate energy type. Right? This was sort of an intermediate energy type. Okay. So you can consider this energy conversion directly. Right? This much of kinetic energy is converted into this much, like 1.1 kinetic energy. Right? So if you consider the initial situation you have initially, you have this way 9.4 speed. Finally, you have this way 1.1 speed and you have a certain height. Okay, so you can say kinetic energy initially is equal to kinetic energy finally plus gravitational potential energy finally. So half into what's the mass? Let's say mass is m. 9.4 squared equals half into m into 1.1 squared plus m into 9.81 mgh. So you can get h easily. Now you might ask, why don't we use elastic potential energy in the equation? That is because initially also the elastic potential energy was 0. Finally also the elastic potential energy is 0 because the pole is at its maximum height. Initially the pole was just laying on the ground, laying in the athlete's hand. No extension. Right? But in the middle of the process, there was a certain conversion of elastic potential energy. It gained certain elastic potential energy and it lost certain elastic potential energy. So when you consider the initial and final situation, we don't need to consider them. So you can get the maximum height. You can calculate and get it. Okay. Consider the pole to behave as a spring of stiffness 850. The distance between the two ends of the pole decreases by 2.1 during the jump. Yeah, there's a certain kinetic energy stored in the pole as well, right? Yeah, so you can use this E is equal to half F delta X equation. Mhm. Yeah, so like here they have asked this like calculate the maximum proportion of initial kinetic energy stored by the pole. This is the process, right? You have kinetic energy converted into elastic potential energy, right? So elastic potential energy increases and kinetic energy decreases, and then elastic potential energy decreases and gravitational potential energy increases. That's what happens. So elastic potential energy increases and then all of it is lost. So in the initial stage, when elastic potential energy increases, right, its stiffness is this much and extension is this much. So you can calculate the elastic potential energy, half kx squared. And then also you can calculate the initial kinetic energy, half mv squared. Mass is given, you know the velocity is 9.4. And they ask in calculate the maximum proportion of the initial kinetic energy stored in the core. What is the proportion? Proportion means half kx squared divided by half mv squared. Simply the percentage of kinetic energy which was stored as elastic potential energy. That's what they have asked. See this one. Maximum proportion. Percentage of elastic energy from the kinetic energy is stored. So we have calculated this thing, don't worry. Right? We can use both these equations, but it's better if you use this equation. So like using half kx squared or half fx is the same thing, right? We can get this answer is equal to k is 850 into 2.1 square. So you'll get this answer on 1874.3. You get that answer. And then you can get the kinetic energy. So you can just divide and get the percentage. That's it. Right. So the final question. State and explain two properties that should be considered when selecting a material for the pole. So you can talk about this, right? Because you have knowledge on materials, right? So just think of the properties which are available. You have yield strength, ultimate tensile strength, elastic limit, okay, and Young's modulus. Likewise, you should just explain them. See, they have given property strong or high ultimate tensile strength. So it does not break or fail or snap under a large force. This is one thing. Right? So what you should do is, I mean, even though you know what is ultimate tensile strength and where in the graph it is available, still you don't know where we should apply them in questions. So it is very important to revise these papers, revise these mistakes in the papers you have done. And via these revisions, since I'm discussing, I'm sure that rather than you doing this alone, you have got a good idea, right? So due to that, take advantage of that and revise them more properly. Like you should just sort of memorize. So you should be like just by, I mean, instinctively, you should be able to recognize like where I should apply this, where I should apply this and that. So to do that, you should do more and more papers with proper discussions, right? So now you know if they ask about properties, we can say that the material should have a stronger tensile strength. So the explanation is because it does not break under large force. That's true because you know the theory part, but you don't know where to apply. That's why you haven't done this question properly. This last question, right? If you have given one property, explanation, and another property and explanation, you might have got 4 marks. Okay, these are the mistakes that you do in the exams as well. Like if you just stay at home and do papers for the marking scheme, understand that's no use. You should be able to do under pressure. It's not that that's no use, like that's also useful for knowledge, but not for being right, getting used to exam conditions. Another property is low density, right? So if the low density or if you have low mass, then we can make this energy conversions more efficient. We can make the energy conversions more efficient. High elastic limit. So this one you can tell because it was asked in the earlier question regarding the guitar as well. So the ball does not bend permanently. If you take a guitar, if it has high elastic limit, also we can say it won't deform. Okay. Low elastic material, Young's modulus is better. Okay, right. So I hope this discussion is okay. And if you have any doubts, even after this watching this video, just note them down. Just as you like, while watching the video, please note down the doubts you didn't understand. First of all, try to go back, watch it again. And even in that case, if you didn't understand, just mark those doubts and we'll discuss them in the next class.